let's continue part 2, lecture 2. Okay? Now, curvilinear coordinates, covariant base vectors. Covariant base vector, I'll talk to you, is AI. I'll talk this. Why it's called covariant base vector. Now, I want to display, okay, two particular cases of curvilinear coordinates. You see, the first one, I'll be lecture 2.1, cylindrical coordinates. Okay? Previously, we talked about the rectangular coordinates. Okay? We already showed the lecture. Okay? Part 2, lecture 1A, 1B. And you see, again, a point, okay, employing the cylindrical coordinates, it can be obtained by the intersection of three surfaces. The one is a cylindrical surface. This is a cylinder, radius rho. The other surface is a plane. The plane, this theta, is an angle between the x-axis and the line over here. Okay? This is theta. That's over here. We call a polar coordinate. Okay? The orange, just to rotate the angle theta, the orange is in the plane x and z, or x1 and x3. Don't forget that this is x1, and this is x3. Okay? And also the orthonormal basis is E sub 1, E sub 2, and E sub 3. I'll write here E sub 1, this E sub 3, and this is E sub 2. Okay, don't forget that. You already did show it, okay, in lecture 1A and 1B. Now we are talking about three surfaces. The third one is also a plane which is parallel to the plane formed by x and y. Okay? If you look at the corner of your room, you see, this will be the floor. Okay, just for you to understand. Okay, these are the three surfaces. Okay, the intersection of these three surfaces will be a point. Okay, the point is written right here. You see, as a point depends on the radius rho, the polar angle theta, and the height z. This point here is an intersection of these three surfaces, okay? Which you can look at here. You see, I have a cylinder of radius rho, okay? Radius rho here, we bring it here. I have a plane whose orange is x and z plane. The orange, okay, rotate, okay? I would say rotate counterclockwise, okay, by convention. And this is the height. So the intersection of these three planes, three surfaces, okay, two are plane, but cylinder is not. So say this the intersection lead to the point P, which a particular case, P, A, B, C, you see, is given by rho is equal A. That's a specific point, okay? Theta is equal B and C is equal C. You see, this will be rho, this is theta, and this is Z. That's convection. You see, intersection of three surfaces. Which surface? Okay, the cylinder of radius A. We call the polar angle theta, which is equal B. Theta is measured in radian, obviously, okay? And also Z is equal C. See, C is the height, okay? So that's why I can write the intersection of this. You see, this figure exactly like that one. Now I will, in this case, I will insert, okay, the base vectors. You see, look at, it's very interesting. Sometimes it's confusing. This vector over here is rho, is the intensity, the size of the vector, is the magnitude. In this case, rho, E rho is this size here. This vector here, the vertical one, is Z, okay? Now attention now, EZ in cylindrical coordinates has the same notation of E3. Don't forget, okay? Now in the traditional notation, this is the orthonormal base K, and this is the I, okay? The orthonormal, okay? So I'm going, but attention now, the vector R, the position vector of this point P here, okay, the P here, now it's general, okay, I'm not talking any point, so I have to have rho, theta, and Z, which correspond to three surfaces. Again, I'm repeating again. So rho is equal R, is vector R, position vector. It's rho, E rho plus Z is Z. You see, well, attention here. You see, you don't see here the unit vector theta, okay? You don't see here. But you can write this, you should write this, just is the sum, okay, a vector sum between this vector here is rho, E rho, plus Z is Z, so it's there. Now, look at how it's interesting. This over here is the same vector, you see, is invariant. It's the same vector, R, position vector, expressed by the rectangular coordinate. The same vector, okay? This vector can be expressed in cylindrical coordinates and also, or let's say this, in Cartesian coordinates. The same vector is invariant. What is invariant? If you change the coordinates, the vector remains the same. It's very, very important. Okay? Now, I can relate, okay, the rectangular coordinates to the cylindrical coordinates. Look at that. X is rho cosine of theta. You see, look in here. It's quite easy. You see, look. I'll leave here a space just to write the figure for you to understand clearly. You see, look. Let's look. It's interesting. Let's look here on the floor. Okay, I just write X and Y, or X1 or X2. I'll put this floor right over here, just for you to understand clearly. This is X, okay? I call x1. This is y, which I call x2. Now, you look at this figure. Let's call this point here point Q. Q is on the floor. So this I have, it's quite clear. Q is on the floor. I'm just represent the floor over here. It's point O. Okay? Now, you look at here, you see it's better. You see this is rho. Okay? Rho. P I put over here just to not be confused. This is my point Q. Okay? Point Q. P is the space. Q belongs to this plane X and Y. Now, I look at here and I'll put this rectangular triangle. Okay? Here is my angle theta. And OQ is rho. You see, OQ, the intensity, the magnitude, this is rho. Okay? Then I can see here my unit vector. No, I'm sorry, no, it's not necessarily unit. Attention now, please. Orthonormal basis, it's here. Cylindrical coordinate, in general, they are not orthonormal. Okay? The base vectors, they are orthogonal, but they are not orthonormal because it's not the intensity of the base is not